Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue our conversation about optimization problems within a differential calculus class. We have already done kind of the tactic for solving these optimization problems. We've talked about maximizing areas and minimizing distances. Now let's talk about volumes. Each of these problems is basically the same thing over and over. It just comes down to you drawing pictures and doing things kind of carefully, right? So maximize the volume of a cone inscribed in a sphere of radius 1. So there is one thing you're really going to need to look up here. It's the volume of a cone. That's going to help out. But I've read this problem. I'm now going to draw a picture to help me understand what's going on. So I start with the fact that somebody's handed me a sphere. Let me go ahead and just show you that this is a sphere. It's a three-dimensional object. Back behind, it just kind of rotates around, that type of thing. And so we have a sphere, and inside this sphere, this ball, we have a cone. So let me go ahead and draw a cone. There we go. We have a cone sitting inside that sphere, and we just want to find out where can we, or what size cone, or what's the maximum volume of a cone that can be placed in this. Obviously, there are all different types of cones that can sit in here. For example, I could have a cone that did this. That's probably has more volume to it, something like this. So that's just a heads up that really this is a representation of a single cone. This is an arbitrary cone, but obviously this is not the one with the maximum area, but that's not what I'm concerned about. I'm actually just concerned about drawing a picture and making sure that we understand what's going on. So how do you find the maximum area or the maximum volume of this cone? Inscribed in a sphere of radius 1. And that sphere of radius 1 is incredibly important in this problem. It doesn't have to be a radius of 1, by the way, but it does have to be a stated radius. So let me go ahead and draw in the radius. And the radius I'm going to draw in will connect from the center of the cone, or sorry, from the center of the sphere to the edge of the cone. So from the center here all the way to this edge, and also actually to the top of the cone. I'm going to go ahead and connect that to the top. Obviously I slightly missed there, but whatever. So those red distances are distances of length 1 because they're along the radius of this cone. There we go. All right, so how in the world are you going to find that volume? Well, I'm not going to worry about that yet because I need to actually know the volume of a cone first. And that is, you can totally look it up if you want to, but the volume of a cone is 1/3 pi r squared h. That's one that I often forget myself. So usually if I have to if it's on an exam, I generally give my students that formula if it's on an exam. Notice that master equation for the volume of the cone has way too many variables. And by the way, r there, that r is the radius of the base of the cone. Let me go ahead and draw that down here. It is the radius of the base, or the length of the base of the cone. So that's r right there. The height of the cone is all of this distance here. It's the total height of the cone. So this all the way down to here would be the total height of the cone. Problem is the total height of the cone is that 1 plus x. Now, one thing that we have to agree upon here before we continue forward in this problem is that likely the largest volume you're going to get is going to occur when x is greater than 1. It doesn't have to be, though. We could still do this problem with x being allowed to be negative. Sorry, not x being greater than 1, but being greater than 0. So the fact is, we could allow x to be negative, and if we did, we just would have a cone that would look something like this. And it would connect up to these spots right there. But that doesn't look like it would be an optimal situation, but we'll allow for it in the mathematics. All right, So if I want to find a relationship between the base radius of that cone and h, I had better figure out a formula here. Well, h is equal to 1 plus that x value, right? So at least I could sub that in. I can say volume is equal to 1/3 pi r squared times 1 plus x. But now I still have too many variables, v, r, and x. Maybe I could find another relationship, this time between r and x. And if you look at my drawing, there's actually a right triangle right there. X is the side length, r is the side length, and 1 is the hypotenuse of that right triangle. So this is another relationship. 1 squared is equal to x squared plus r squared. Or in other words, wherever I have an x, I can solve for that and replace. In fact, you know what I could do? Instead of solving for r or for x, I'm going to solve this for r. Because notice in my equation, v is equal to 1/3 pi r squared times 1 plus x. But the reality is, I don't want to sub out x. I'd love to sub out r squared because r squared is simply 1 minus x squared. So that's what I'm going to do. Rather than subbing in for x, I'll sub in for r squared. R squared is 1 minus x squared, so this means the volume of that cone that's inscribed in that sphere is 1/3 pi times 1 minus x squared times 1 plus x. That's just a polynomial. I could totally multiply that stuff out. So this is going to be 1/3 pi, and that'll be, let's see, a negative x cubed minus x squared plus x and plus 1. All right. Well, let's go ahead and find out what the critical numbers of the volume is, or are, I should say. So v prime is equal to 1/3 pi, let's see, negative 3x squared minus 2x plus 1. And we want to find out when that doesn't exist. It always exists. Or when it's equal to 0. Well, v prime is equal to 0, finding the critical numbers, when 3x squared plus 2x minus 1 is equal to 0. Now, I'm going to guess that that doesn't factor, but I'm just going to try anyway. 1 and x, 1. Let's see, that's plus, that's minus. Wow, that actually does work. Sweet. So either x is 1/3 or x is a negative 1. Now, think about this geometrically. X is the extra distance that we have gone from the center. So we either go down a distance of 1/3 and create a cone there, which is a big old cone, isn't it? Or we let x equal a negative 1. In other words, we go all the way back here and make a cone at this little dot. Well, that's ridiculous. That little dot, there's no volume to that dot. So, draw this out. X can only go from negative 1 anyway, all the way up to positive 1. X can't be greater than that because x is constrained to go from the top of this ball to the bottom of this ball. And it's centered at the center. So x is just a distance from the center. So it can be negative 1 or positive 1, but it can't be anything beyond those values. So we have 1/3 as a critical number. Let's find out what the derivative, what the signs of the derivative are in these intervals, or what the sign of the derivative is in these intervals. Geez, I'm terrible. All right, so let's see. Plug in 0, v prime at 0 is a perfect one to plug in. If you go to v prime here and plug in 0, you get positive. So there we go. The volume is increasing. And then if you plug in a number beyond 1/3, but less than 1, so try, I don't care, 2/3. Actually, technically, you could plug in 1 if you wanted to, but I'm not going to. Plug in 2/3, and you will get 1/3. All I need to know is it positive or negative. So v prime at 2/3 is going to be 1/3 pi times -3 4/9 minus 2 2/3 plus 1. And when you multiply this out, you get -12. This is a -12/9, which is actually less than 1 already, and you're losing more and only gaining back 1. It is negative. So the volume is decreasing on that interval. So the volume was maximized when x was 1/3. Find the maximum volume now. Well, to find, we get an absolute maximum when x is 1/3. And that volume is, let's see, where's our volume formula? Just in terms of x's. So I'm going to plug it into this right here. I'll just plug in 1/3 into that formula. So volume at 1/3 is 1/3 pi. Let's see, 1 minus 1/9 times 1 plus 1/3. Now I'm going to go ahead and finish this out. That's 1/3 pi, 8/9, and 3/3 plus 1/3 is 4/3. So it's 32 pi over 81. Whatever that number is. But that's the maximum volume. That many cubic units. I have no idea what units we were dealing with here, but that many cubic units is going to be the maximum volume. Really cool problem. The second and only other volume problem that I'm going to deal with is this guy right here. It's such a fun problem. You have a cone-shaped cup, like you get slushies out of it or something like that. It's made from a circular piece of paper of radius 5 by cutting out a sector and joining those edges. Find the maximum capacity of such a cup. The thing here is that they didn't tell you what size the sector was that you cut out. So let's go ahead and visualize this. I'm going to create a circular piece of paper, and I'm not going to have this piece of paper go all the way around. I'm just going to go partially around. So maybe to there is a good idea. And I will turn to my ruler, and I will just cut out that sector. So let's go ahead and cut this out. Whoop and whoop, right? So then what you would do with this is you would fold your piece of paper and connect those two edges, and you'd create a cone, right? And this length, by the way, let me go ahead and just turn that off. This length is 5, of radius 5. Again, nobody tells us any units. 5 inches, 5 feet, what do you got? Okay, we're gonna cut out a sector, which is what we've just done, and we're gonna join those edges. So then you get a cone, right? When you join those edges, there you go. Well, that was a terrible cone. I freehanded that, sorry about that. And let's see if I could do this a little bit better. Well, it's a little bit better. Okay. So these two edges here will be glued together. The question is, what is the maximum volume or capacity of that cup? Well, from the last problem, we know that the volume of a cone is pi r squared. I'm sorry, it was 1/3 pi r squared h. 1/3 pi r squared h. And let's see the things that we don't know here. When you fold that paper together, that length of 5, maybe I should do this in green, this length of 5 right here, and obviously this length of 5, they get snapped together and they become the length of this edge. So that edge length is actually 5. Okay, so that helps us out slightly. And you'll have a height to this cone. And there's a right triangle right there. I'll just call that height h because that's part of what we need. And we'll have a radius for that cone. Again, we don't know what that is, right? In this case, Pythagorean theorem looks to be a very useful relating equation. So we could say that r squared plus h squared should be the same thing as 25. And therefore, whenever I see an r squared, I can replace it with 25 minus h squared. So this is looks very much like the previous problem. And it kind of is. There are other ways you could do this problem. By the way, you could possibly use angles here, and that's kind of what I wanted to do, but now that I'm thinking about it, it might be easier to do it this way. R squared is 25 minus h squared times h. And now you could find the critical numbers of this by distributing that h through and then taking its derivative, right? So v prime is equal to 1/3 pi, and then we have 25 minus 3h squared. Kind of quick problem. And so this is equal to 0 when, let's see, h squared is equal to 25/3, or in other words, h is equal to 5 over root 3. And now we go ahead and draw out a number line here. The height of this cone will go from 0 to a maximum height of, let's just say 5, even though that's not going to be realistic, but from 0 to 5. So I'll just say from 0 to 5, even though it will never be a height of 5, because that just means you're folding the cup, you're cutting the entire cup away, basically. Remember, the radius, this length right here, is 5. So that's always the longest edge of the hypotenuse, is always the longest edge of a triangle. So that height at max could be 5, and it's not even going to be 5. And then our critical number, 5 over root 3. So let's go ahead and try numbers less than 5 over root 3 and greater than 5 over root 3. 5 over root 3 is roughly 2.9. So I'm going to plug in 2 into our derivative formula. If you plug in 2, so b prime at 2, you will get 1/3 pi times 25 minus 2, 4, 12, 13, which is positive. It doesn't really matter. So it's positive. So at that point, our volume is increasing. And then if you plug in a number greater than 2.9, so like 3, you'll have 1/3 pi 25 minus 27, which is a negative 2, and so that's negative. So we know the volume is decreasing. So we've found the max. The maximum occurs, the maximum volume of that cup occurs when the height is 5 over root 3. Luckily, they didn't ask for a lot of information here, but we do need to actually compute the total volume. So the volume at that 5 over root 3 value is roughly, and I'm just going to use my calculator for this, it's roughly 50.4, and that's cubic something. They didn't really quite say exactly what it was, but it's some cubic inches or something like that. The interesting question here, which I think would be very tough initially to think about, is how is the angle theta that we cut out, how is that related to that volume? The way I'm thinking about doing, if I were to do that, I would think about, not that I'm asking you to do this, but the way I would do it, now that we know what the volume is, I would relate that to surface area. And surface area you can write in terms of this theta here that I just erased, but you could write it in terms of that theta, and that would be the link. Not that I'm asking you to do that, but I was just kind of brainstorming. Anyhow, this is the last problem that I have for the volume. So there you go, maximizing volume problems.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.